Hey there, welcome back to our channel. If you've been following along, you'll recall that in our previous video, we demonstrated how to create a point light model in WebGPU. A point light behaves like a light bulb, emitting light that gradually fades out as it travels further away. Point lights are commonly used to simulate non-directional light sources, such as light bulbs or ambient lighting. In today's video, we're going to delve into another frequently used light source known as the spotlight. Unlike the point light, a spotlight is a directional light source that emits light within a cone-shaped beam. It possesses a specific position, direction, and a cutoff angle that determines the extent of the light spread. Spotlights are ideal when you want to concentrate light on a specific area or object, generating highlights and shadows with a focused beam of light. The examples of spotlights include flashlights and street lamps. Like point lights, spotlights also exhibit attenuation, where the light intensity is highest along the axis of the cone and gradually diminishes towards the outer edges, resulting in a realistic spotlight effect. In WebGPU, a spotlight can be defined by its world space position, direction, and cutoff angle. When processing each fragment, we determine if it falls within the spotlight's cutoff directions. If it does, we illuminate the fragment accordingly. This illustration picture should give you an idea of how a spotlight works. In this image, the blue lines depict the light direction, extending from the fragment towards the light source. The red line represents the spot direction. The angle phi denotes the cutoff angle, which determines the radius of the spotlight. Anything outside this angle remains unlit by the spotlight. The theta angle signifies the angle between the light direction and the spot direction. In order for a fragment to be illuminated by the spotlight, the theta value must be smaller than the cutoff angle phi and should fall within the spotlight cone. So what we need to do is to calculate the dot product between the light direction and the spot direction and compare it with the cutoff angle phi. Alright, let's dive into the programming aspect now. We will start with the project we worked on in our last video. If you already have the project on your local machine, simply open it using Visual Studio Code. If not, don't worry. You can easily download the project from our GitHub repository using the command git clone followed by the branch name and the repository URL link. This will download the project onto your local machine. Simply open this project using Visual Studio Code, and then use the command npm install to install all npm packages required by this example. Now, let's implement the spotlight model in the shader code. Create a new fragment shader file called spotfrag.wtsl in the section 02 folder and insert the following code into it. This fragment shader closely resembles the point light model we covered in our previous video. However, the main difference lies in the calculation of the angle between the light direction and the vector connecting the spotlight to the fragment. We then compare this angle with the cutoff angle. If the angle is smaller than the cutoff angle, we consider the fragment to be inside the spotlight cone and apply ambient, diffuse, and specular lighting calculations. Additionally, we incorporate attenuation, which is similar to the code used to calculate attenuation for the point light in our previous example. On the other hand, if the fragment falls outside the spotlight cone, it only receives weak ambient light, providing background illumination. Now, add a new TypeScript file named spotlight.ts and paste the code to the file. This example follows the similar structure to the one used in the previous video. The create pipeline function has been updated to accept an additional input parameter, the number of objects parameter, which represents the total number of instances for all types of shapes in this demonstration. Inside the create pipeline function, we generate vertex, normal, and index buffers for the cube and sphere shapes. We then define the uniform and storage buffers for the transformations and colors. Here, we utilize the create buffer function from the WebGPU simplified package to create storage buffers by specifying the buffer type enum as storage. Within the draw function, we begin by rendering the cube instances, followed by the sphere instances. Using this code snippet, it is important to set the first instance parameter accurately to avoid instances overlapping each other. In the run function, we create total of 200 instances, including 100 cube instances and 100 sphere instances. This code block allows us to define the model and normal matrices, along with color for each instance using the random math function. This will create a distinct location, orientation, and color for each instance. Note that in addition to light position, we also define light direction variable that represents the spotlight direction. This is different from the point light we discussed in the previous video. Here, we have added the linear, quadratic attenuation, and cutoff angle parameters for the spotlight to the decay control, which allows us to examine their effect on the light by changing the parameters with the mouse. We have also animated the position of the point light source within the frame function, so you can see real-time changes in the lighting effect in the scene. Now, let's proceed to add this example to the navigation menu. Open the side-nav.html file from the src.html folder and add the following link spotlight. Once we have done, we can proceed to build and compile the code by executing the command npm run prod in the terminal window. Then, clicking on the Go Live to open the default web browser and view the 3D objects with spotlighting in action. You can see that only the objects within the spotlight cone are illuminated, while the objects outside the cone receive only weak ambient light. You can change the cutoff angle to examine the effect on the spotlight. It is important to mention that the spotlight model we are discussing here exhibits a hard edge, resulting in an abrupt cutoff of light beyond the spotlight cone. To achieve a more realistic spotlight effect with a smooth attenuation around the edges, a two-cone approach can be employed to create a soft-edged spotlight. However, I won't be covering this particular model, as well as other light models like directional light and fog effects, in this video series. If you are interested in learning more about these light models, I recommend visiting the following website for a live demonstration. It provides a comprehensive overview of these concepts and their practical implementation. Now, let's conclude today's video. In the next installment, we will discuss the shadow model in WebGPU. Make sure to stay tuned for that upcoming video. Thank you so much for watching today's video. I hope you found it informative and helpful for your WebGPU development journey. If you enjoyed this video, please give it a thumbs up and subscribe to our channel for more exciting content. If you have any questions or comments, feel free to leave them down below. Until next time, happy coding!